What happens when an AI does exactly what you told it to do, but completely fails the task that you actually wanted it to accomplish? In reinforcement learning, this is called reward hacking or specification gaming. This is what happens when an agent finds a loophole in your math and exploits it to get high score. Today, we will see a physical manifestation of this problem using this device that I call the light seeker. It's designed to mimic a solar panel tracking down ambient light to maximize energy intake. But, as you're about to see, giving an AI a simple task in a physical environment can lead to spectacular, unexpected failures. Let's take a look at the hardware. We have an ESP32 microcontroller acting as a brain, driving two servo motors for pan and tilt articulation. At the top of the moving platform is a simple photoresistor measuring the intensity of light. To control the device, we are using Tabular Q-Learning. Because a microcontroller has highly constrained memory, we cannot tell it to process infinite, continuous physical environment. Instead, we discretize the servo's range of motion into 15-degree increments. This creates a 12 by 12 grid of possible states. The process has two phases. First, training. The device scans the environment, logging the light levels at every coordinate. Then it runs a value iteration algorithm, essentially playing out thousands of moves in its head to build a Q-table of optimal actions. Second, inference. Once trained, you can point the device anywhere, and it will use that Q-table to flawlessly navigate step by step to the brightest spot in the room. Or so you would think. Let's look at what happens when we set the reward function to care only about the voltage coming from the light sensor. Instead of looking up at the ambient room light, our intended goal, the agent immediately points straight down and locks onto the power indicator LED on its own baseboard. Why? The inverse square law of light. Because the onboard LED is only centimeters away from the sensor, it appears exponentially brighter than the actual ambient light source across the room. The agent isn't broken. It's perfectly optimizing for the proxy metric we gave it, the sensor voltage, while completely ignoring the actual objective, maximizing the energy intake from the ambient light. To fix this proxy alignment problem, we need to turn this into a multi-objective reinforcement learning task. We don't just want the agent to find bright light. We want it to find bright light while looking up. We achieve this by assigning weights to our attention budget. But we can't just multiply raw sensor values by spatial coordinates. The massive analog to digital readings would overpower the tilt indices. First, we mathematically normalize both the voltage and the physical tilt to a scale of 0 to 1. Then we apply a convex combination of weights that must sum to exactly 1. For example, we tell the agent to dedicate 80% of its attention to the light intensity and 20% to maintaining the high tilt. This solves our immediate problem. But let's be clear, this is a patch, not a silver bullet. The fundamental issue is that the precise modeling of physical reality is impossible. If we wanted to model the continuous, messy reality of the physical world accurately, we would need deep Q-learning, or DQN. But executing neural networks of that size would require computing power far beyond an ESP microcontroller. As long as you're using a proxy metric to model the complex physical reality, there will always be edge cases that your model can exploit. Furthermore, while this experiment is framed as a solar panel, Q-learning is a terrible way of building a real solar tracker. This algorithm works beautifully in stationary environments where the light source doesn't move, but the sun does travel across the sky. A Q-learning agent would have to continuously rescan and relearn the environment every hour, wasting power and computational resources. I also need to offer an honest engineering disclaimer about how this demonstration was programmed. True exploratory Q-learning on physical hardware would require the agent to perform thousands of trial and error movements to calculate rewards. If we forced these basic plastic servo motors to do thousands of iterations to complete the Q table, they would strip their gears and burn out in a matter of hours. Instead, the firmware does a single systematic grid scan to map the rewards into memory. The 1000 value iterations, the actual learning, take place entirely in the microcontroller's RAM, simulating the physical moves mathematically. Only the final, optimal policy is executed physically. So, what does the light seeker actually teach us? It's a perfect physical demonstration of Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Machine learning models are notoriously brittle. They don't have common sense. They don't know what a solar panel is. They don't know what the sun is. They only know the math you have given to them. And as we saw today, whether you are dealing with a massive billion-parameter large language model or a tiny microcontroller with 2 kilobytes of RAM, the alignment problem is exactly the same. Getting the AI to do what you want instead of precisely what you asked. If you want more details, the full firmware source code and the technical field note are linked in the description below. If you find such AI fragility breakdowns interesting, stay tuned, and I'll see you in the next one.